In the previous chapter, we took a function of multiple input variables, such as f of x comma y, or f of x comma y comma z, and we took the Calc 1 concept of derivative. We made it work for these new functions, but we had to make a thing that was called a partial derivative. Then we looked at two optimization methods. One used this thing called the second derivative test, and the other was the method of Lagrange multipliers as applications of partial derivatives. In this chapter, we're going to take the same type of function, so a function with two input variables or three input variables, and we're going to talk about integrals. Now, more specifically, we're going to talk about double integrals or triple integrals, and more generally, we're going to be talking about a thing called an iterated integral. Later, we will do some integration using polar coordinates and related coordinate systems. And at the end of the chapter, we're going to talk about a multivariable version of U substitution. So a way to do integration multiple, like a double integral or a triple integral with a thingy that's like U substitution. And then, so that's just trying to be a summary of chapter 15. And then in the chapter after, in chapter 16, much later, we will connect the partial derivatives from chapter 14 and the iterated integrals from chapter 15 in theorems which are multivariable analogs of the fundamental theorem of calculus. There will be at least 4 theorems that are like that. Again, that's for way later, but just wanted to provide some context. So we're about to start chapter 15, and so that in the middle you see that paragraph that's trying to provide what chapter 15 is about in a nutshell. First, let's review the definite integral from Calc 1. So if you are given a function y equals f of x, and you integrate from a to b, from x equals a to x equals b, that is of course the area under the graph, or area under the curve, right? So the region that's shown in blue, you know, from x equals 0 to x equals 8, so this would be integral from 0 to 8 of whatever the function f is that's shown in black there. Now, how is this area computed? We have this calculus way of doing things with an antiderivative and so on, sure, but the first way that we really start to get a handle on and figure out how this area is computed is we first approximate the area using these Riemann rectangles, right? So in every, we just cut up the interval, let's say from 0 to 8 in a bunch of individual little pieces, and in each of these individual subintervals, we just pick a height, and that height should be you know, based on the graph, like at one point somewhere within the interval. So it appears here that it's just within this first interval, just the midpoint, and then whatever the y coordinate is there here at the midpoint, whatever the y coordinate is. That's one way to do it anyway. So what you really do is you just add up the area of n rectangles. Of course, that's not identical to the area under the curve, but we're getting there. So recall that each rectangle has width delta x being b minus a over n. So b minus a is the width of the entire interval, say from 0 to 8, so 8 minus 0, right? And then you divide by the number of intervals you have. We have 4 intervals here, or 4 rectangles, so 8 minus 0 all over 2 would be 4. Sorry, 8 minus 0 all over 4, there are 4 rectangles. That'd be 2. So each individual rectangle has a width of 2. And then the height is determined by a y value. So it's f of something, where that something is any x value that's in the ith interval. And then here's the point is, when you look at that y value, so f of x star sub I, that's how we write the y value, times delta x, that's the width of the rectangle, then underlined, you see it's the area of the ith rectangle, but then we have many rectangles, so we add up things that look like that. So I going from 1 through n, we just add up a bunch of rectangle areas. So think of, there's 2 sets of underline, so apologies for how this looks, but the inner underline thing that says labeled with area of ith rectangle, so that's like, you know, the area of the first rectangle, or area of the second rectangle, or area of the third rectangle, or the area of the fourth rectangle. And then when you put that sigma notation in front, then we're talking about adding up the area of all 4 rectangles. Okay, but that's still approximate. And then how do we get an exact area? Well, we should just keep making the approximation better by using more rectangles, more intervals. And so then n needs to increase. So if you take a limit of this as n approaches infinity, that is, if that limit exists, then you get the value of the definite integral. Now, in Calc 3, given a function z equals f of x comma y, so there's a graph, and let's say you have x going from a to b and y going from c to d, then we're going to ask what is the volume under the graph. So here, for instance, this wavy thingy is trying to be a picture of a surface, or it's really supposed to be the graph of function f of x comma y in three-dimensional space, and we're asking under that what is the volume there. And here's a different picture for different functions. So you see sort of in the thicker black it's sort of a little wavy, and that's meant to try to evoke the image of the graph of some function f of x comma y. And what's the volume under there? Well, it can be approximated by a bunch of rectangular prisms. So you imagine, just like earlier we cut up the x-axis into a bunch of smaller intervals, now you have to cut the x-axis up and the y-axis, and so you get a bunch of, I guess, French fries of perhaps various heights. If there are m sub-intervals in the x direction, then the x direction width is going to be b minus a over m. If there are n subintervals in the y direction, then delta y, sorry, typo, delta y is going to be d minus c over n. So then delta a, that is meant to be the product of a delta x and a delta y, or a delta y and a delta x, doesn't matter the order. So here's like this dotted line from here to here that represents delta x, and then from here to here represents delta y. So then this, it looks like a parallelogram here, but it's just due to the perspective, this little rectangle down here, that's a delta A. Then within, somewhere in there, you pick, a certain x comma y, so that's an xi star and a yj star in there, and for there you apply f to that and you get a z value. So then that's going to determine the height of that French fry. So then the approximate volume looks like this, right? So it's for the height, then the width and the length. So, you have the volume of an individual French fry, and then you need to add up in two directions. And if you take a limit of this as the number of subintervals in x and the number of subintervals in y grows, so m and n should both go to infinity, if that limit exists, then that's the exact volume. And when that limit exists, then we call this volume a double integral. And so it's integral from c to d of integral from a to b of f of x comma y dx dy, or as a bit of a shorthand, just like this delta a, earlier we had delta x become a dx once in the integral. Similarly, we'll just often write a double integral symbol, so it's two integral signs right next to each other, and right underneath we'll tend to write r, meaning this geometric thing down here we'll talk about in a second. Same function that we're integrating, f of x comma y, and instead of writing dx dy separately, we tend to sometimes as a shorthand write dA. So in this second integral, that r, x goes from a to b and y goes from c to d. And this is what, for those of you who are familiar, is called a Cartesian product, if you've heard of it before. If not, don't worry about it. But what it really is, just to break it down, it's the set of all the points of the form x comma y, where x is in this first interval and y is in the second interval. Oh yeah, okay, and then just, I think I said it, but just to make sure, dA is shorthand for dx dy or dy dx. Now, the double integral of z equals f of x comma y over the region R, let's say it's this rectangle here, so a, b, that interval, Cartesian product CD. So here's a picture of that rectangle, that's the Cartesian product, in just the input space, just using the x and y axes. So, okay, it's written like this, as we saw earlier. The dx and dy are written separately when each of the two integral symbols show the endpoints of integration. So we see here this x going from a to b, and then the outer part, this dy, going from y going from c to d. dA tends to be written when there is a single letter, such as this r written below, to r alone, r I guess for rectangle, trying to represent the shape. Think about back in Calc 1 or 2, the integral of f over the region. So we would say the integral from a to b of f of x dx is the integral of f over the one-dimensional region, the interval from a to b. And so just trying to connect it to, like, over here now, the integral, when there's two input variables, the integral is over a two-dimensional region, like a rectangle. Okay, so that's really the only key difference.